All right, so I've started the recording, and I'm going to post this on our YouTube video later. If you want to find that, just Google SPEDAS YouTube. That's how I find it. All right. So looks like we've leveled off with participants. So let's go ahead and get started. So if you have any questions, feel free to unmute and ask during the presentation. But if you do unmute and ask, you're going to be recorded, and that'll probably be posted to YouTube too as well. So if you don't want to be recorded, you can always just email me. My email is right here at the top, egrimes@igpp.ucla.edu. And so for the agenda, we're going to be I'm going to be introducing a new matplotlib version of pytplot. So it's a new backend to pytplot that uses matplotlib instead of Qt. And then we're going to show ephemeris and coordinates data, fields data, energetic particle data, that's the FEEPS and EIS instruments, plasma data, just the FPI and HPCA instruments. And then we're going to show how to save figures using a bunch of different formats. And so as an introduction to the, so if you've used pySPEDAS and pytplot before, you've probably used the Qt version, and you probably ran into a lot of problems with that. So those problems led to a new version of pytplot, a new experimental development version that entirely depends on matplotlib to create the figures. And we just eliminated the Qt backend for this. And so we're doing all the development under the pytplot repository so it's github.com/mavenSDC pytplot. I usually just Google to get there. And once you're actually at the pytplot repository, you just select the branch if you want to look at the code and go down to matplotlib backend. Or while it's still being experimental, you can install it directly from this from that repository. So this is what I'm calling the bleeding edge of pytplot right now. So you just install this zip, and you have to install this zip before you install pySPEDAS. Otherwise, pySPEDAS is going to go out and install the old version of pytplot. And we have several examples of using this. So reconnect. I don't think that's going to matter because I've already ran all the examples. So we have the input, the output, and the plots, even though it got disconnected. So if you go to the pytplot repository and the matplotlib backend, we have some examples of actually using this. Create simple plots, doing various settings, adding variables on the x-axis, plotting a bunch of different variables at once, updating metadata. We're going to show a lot of these examples today, but this has a bunch of complete examples. It's probably has more examples that we're going to show today. And so I guess we can go ahead and get started. So the first thing I did was install the pytplot backend, or the matplotlib backend of pytplot first, and then we install pySPEDAS. I also installed pySPEDAS from the bleeding edge as well. I'm not sure if we require it right now, but there are some, we've been working on it. So there's definitely some updates in the bleeding edge that haven't been released in the official PyPI release yet. So if you want to install the latest PyPI release, you just do pip install pySPEDAS. If you want to install the bleeding edge, you have to do pip install and then give it the actual full location of the master zip. And so once you have those installed and set up, you just to import pySPEDAS, it's just import pySPEDAS, to import tplot to create the plots. You just say from pytplot import tplot. And if you want to get started, if you want to run this on your machine and figure out how to get started, just go to our top level repo. It's github.com/spedash/pySPEDAS. I think I already have it open. We have instructions in the README here. So Python 3.7 or later is required. If you, when you install Python, I suggest using Anaconda to install it. You do get there are some speed improvements here by installing Anaconda, because you get some routines that we some compiled routines with Anaconda that we utilize if they're available. And I'll talk about that a little later as well. And so if you're running in your local machine, you might want to set up a virtual environment to avoid any dependency issues. So we have instructions on how to do that on Windows and Linux, as well as how to tie that virtual environment to your actual Jupyter notebook. You just use these couple commands here. And then you can get started with either installing it from PyPI or installing it from the bleeding edge. And one other thing I wanted to mention was that so if you, by default, the data is going to be stored in the directory that you're running pySPEDAS from. If you want to change that directory, just set the SPEDAS data dir environment variable. It'll create an MMS folder under that SPEDAS data dir environment, wherever that location is, and it'll store all the data from there in there. We also have mission specific data directories, so you can set MMS Data dir and it'll override the directory that you specify in SPEDAS data dir. And we have a lot more examples. We're going to show some, there's some overlap with these, but we have a large number of examples under our MMS examples repository. I showed that for the webinars folder, but if you go to basic, we have all the different instruments. And we also have some advanced notebooks. So for instance, generating spectrograms in moments with the plasma data, doing plasma calculations with Plasma Pi, and wave polarization using SCM data. And one thing I wanted to also point out is that we've had these load routines for loading the segments, essentially the burst segments, the fast segments, and the science region of interest segments, so that users can actually load these different segments and know where the different intervals are. It turns out the matplotlib backend, the pytplot, just supports these segment bars automatically by default. If you tried to plot these with the Qt backend, it wouldn't have worked. But turns out these just work. So I loaded the burst segments, the fast survey segments, and the science region of interest segments for this October 16th date. This is our, if you're familiar with MMS examples at all, you probably know this date. This is the date we use for most of our examples, or a lot of our examples anyway. And one thing to note is that the science region of interests are dependent on probe. By default, I think it does probe 1. But the other probes also have science region of interest segments, which should be pretty close to the, they should all pretty much be the same for the most part.
Question?
Yeah.
It says it's like the first line after the load segments thing. It says file is current and then it's content PyData MMS burst intervals .sav. The Python is loading an IDL save file?
Yes.
Interesting. Okay, thanks.
Yeah, so they produce these burst segments in a large file at the Science Data Center, and we mirror that that file at speedas.org, or not that file, the full file, but just the burst intervals from that file at speedas.org. And then it's going out and downloading that save file. And it's the same save file that we load from IDL as well. In fact, these routines behave exactly like they do in IDL.
Yeah, I just didn't realize that Python could read IDL save sets.
Yep, there's a Python code to do that.
Yeah, cool.
And in fact, pytplot has, if you go to their repository and then go to pytplot and importers, there should be tplot restore, which will load. So if you save a file in IDL using tplot save, this file can actually restore it. Or this routine can actually restore that file in Python.
Get right into Python. Yeah, that's very slick.
Yep. And all of the credit there goes to the pytplot people at LASP, as well as I think they're using SciPy to actually read the IDL files. So the tplot version is essentially a wrapper around SciPy function that loads in IDL save files. So I'm sure some grad student at some point implemented that, and now we're using it. All right, so the load routines in pySPEDAS all follow the format pySPEDAS.mission.instrument. I mean, other than these custom ones for burst segments. But if you want an actual instruments data, it's just pySPEDAS.mms for MMS, and then the instrument name. And all of the load routines accept keywords for controlling which data are loaded. Some of the standard ones for MMS are time range or T range for setting the time range, probe for setting the probe. You can specify an integer or in a string or an array of strings or array of integers. We'll show examples of that. Data rate for setting the data rate, data type, and of course the data type always depends on the instrument, and we'll show a bunch of examples for those. Level pretty much always defaults to L2, but we also have the L1B, L1A, CITL, Quick Look. Those are available as well, but they require MMS username and password. If you try to download any of these without actually specifying a valid username and password, it'll say that the data doesn't exist. We also have a keyword time clip, which clips the data down to the requested time range, and that should not be dash or slash, it should just be time clip equals true. A typo. Should be time clip equals true. So the reason we have time clip is the load routines will go out and look for all CDF files that have data within the requested time range, and then we just dump all of that data into memory. So if you have a CDF file with more data than the time range that you requested, it's probably going to give you more times than you requested. The reason for this is because time clipping the data actually takes time. It can actually take a lot of time. And so sometimes you just want to load all of the data and then zoom into the plot instead of spending all this time clipping the data down to the requested range. So just be aware, if you don't use the time clip keyword, you might end up getting more data than you expect. So for instance, if you request 1 hour of FGM data on a date, it's going to give you the full day of time, or it's going to give you the full day because the FGM data are probably the survey mode FGM data are daily CDF files. So you'll want to time clip down to that 1 hour, or you might want to. We also support the SPDF keyword that tells the load routines to load the data from the SPDF at NASA instead of loading them from LASP SDC. By default, everything's loaded from LASP. And we have a keyword available, which returns a list of files available, the SDC for the requested parameters. So if you set this, it doesn't actually download any data, it just tells you which data would be downloaded. And each keyword has defaults. So if you just call pySPEDAS.mms.instrument, so like FGM, it should load some data. And for a full list of the available keywords, call help on the function you're interested in. So for instance, with the MEC routine, it's just pySPEDAS.mms.mec. And we called help on it. And it shows a list of all the available parameters. And you can see there's more than just the few that we have up top. You can tell it not to load the data in the T-plot, and instead just return the data in hash tables. You can specify version numbers, specific version numbers, minimum version numbers, tell it to only grab the latest version, tell it to only grab the latest major version. If you ever, so if you save your password and you want to, if you accidentally save the wrong password, or if you want to reset, if you get a new password, you can just always set the always prompt keyword. This will tell you to, this will tell the load routine to always ask for the username and password. Otherwise, it's going to save it in your working directory. It's going to save it the first time you specify a password, it's going to save it in your working directory. Yeah. So I guess we can go ahead and get started by loading some MEC data. You just call pySPEDAS.mms.mec. And in this example, we're setting the date to October 16, 2015. So it's a full day, and we're requesting all 4 probes. By default, it just loads probe 1. So you can see that. Let's zoom up a little bit here. See, it requested a password, and I just gave it an empty username and password, and it saved it. So it should just have me authenticated as a public user. And you see it downloaded the files for each probe. So if you run this, if we were to run this again, it would find these files automatically and just load them. It wouldn't re-download them. It caches them and checks that they haven't changed when you load them. And you see it loaded all the variables for all the different probes, MMS1, MMS2, MMS3, MMS4. So if we want to plot the position data, we just call tplot. And one thing to note is that tplot accepts this new experimental version of tplot actually accepts Unix style wildcards for strings. So a question mark will match a single character and a star will match multiple characters. So if you want to plot all 4 probes position data in SM coordinates, you could just say MMS and then question mark and then MET R SM. So this tells it all 4 instruments or anything with a single character here, it matches. So that's the 1, 2, 3, and 4. You can see we have MMS 1 position on top, 2, 3, and then 4. So if you want to list the tplot variables loaded, pytplot has a routine called tplot_names, just like an IDL, and you say tbars equals, and just call the tplot names function. And it lists the full list as well as returns the full list in the tbars variable. And there's a quiet keyword here that you can set to true, and it won't list the variables. It'll just return it to tbar. It'll just return the variables to your in your tbars variable. And I remember I loaded the burst segment bar earlier, so we can go ahead and include that on a figure. So in this case, we plot the burst segment bar up top, and then the 4 spacecraft position vectors in SM coordinates below it. And you can see now the burst mode bar is actually up here. You can see where the burst mode segments are throughout the full day. So we have survey mode data on the bottom, but you can see exactly where the burst mode intervals are up top. And in IDL, we shrink this down quite a bit, but we haven't actually gotten there, gotten to that point yet with this version of pytplot. So the current panel for these bars is going to be the same size as these for now. So if you want to access the actual data in a tplot variable, use get data from pytplot. So you just import it from pytplot and then call get data on the variable you're interested in. And so that returns a named tuple. So the Unix times or the time values are stored in data.times. And these are Unix times or the number of seconds since January 1st, 1970, excluding leap seconds. So it's just data.times for those. And we have routines for working with times. So for instance, if you want to convert a Unix time to a string, use time_string. So you just import that and then call it on the time that you're interested in. Or it also supports an array of times. You could also convert the Unix times or convert from a string to Unix times using time double. So you just import that from pySPEDAS and call it time double on the string you're interested in. And this should match the same one up here. And if you want to work with datetime objects, we also have time datetime. So you just import that one from pySPEDAS and call it on. You can give it either a Unix time or a string, and it'll return the datetime object with the time zone info, with the time zone actually set to UTC. So this is a big warning. If you use datetime objects in Python, be sure to set the time zone to UTC, because for all of these, we're using the UTC time zone. And if you're using datetime objects and everything is off by however many hours you are from UTC, then you've probably forgotten the TZ info somewhere. And so we know how to get to the times. If you want to get to the actual data values, those are stored in data.y. So you can see we have all of the vectors here. I think these are position vectors. Yeah. So we can say data.y.shape. So it's got 2,800 times and 15 actually, no, this is, yeah, that's not going to be correct. Because I actually overwrote my data below, so that's not going to be correct. Shouldn't have used the word data twice in one notebook, but this is data that's going to be later. Let's see. So if you want to access the metadata, you can also use get data for that. You just set the metadata equal to true, metadata keyword equal to true. So this returns the CDF metadata as well as the actual plot metadata in pytplot. And I'll show how to access the actual variable attributes for a variable a little later. So if you want to create a tplot variable, so the opposite of get data is store data. And there's a keyword called adder dictionary that actually allows you to set the metadata from a previous get data call. So all that's actually required to store data, though, is you call store data, you give it the variable name. In this case, we're calling it my new position bar. And then you set the data keyword to a hash table that contains the X value with the times and the Y value with the data values. So that's all that's actually required to create a variable. But I'm also passing the metadata here via the attributes dictionary. That way we preserve the plot metadata and the CDF metadata. And so I plot the new variable. And you can see that it has the position variable, but it also, since I gave it the metadata, it also still has the legend. The colors are correct. The Y title is correct. So if you didn't include this this part here, this metadata part, the legend wouldn't be here and the Y title wouldn't be here. We'd probably just use the variable name and the Y title. I think the colors would still come out the same though, because the default colors are just blue, green, and red for vectors. If you want to change plot options for a particular variable, you use the options function from pytplot. So you just import that from pytplot and call options. I can give it the variable name that you want to change the options for. And then, for instance, the legend names are just legend underscore names. So we can change that to X, Y, and Z. I could change the Y title, change the Y subtitle. If you're interested in all the options available, you could just call help on call help on options function. It should work. And it should list all of the options available. Like you could change the color, you could change the color map of a spectrogram, change the spectrogram from spectrogram to a line plot. So not all of these are supported in the new version of pytplot yet. I think some of them like alt and map haven't actually aren't supported, and I would be surprised if those are supported in the Qt version too. But most are, most that you would want to set, like Y log, Z log, Y title, Z title, Y subtitle, Z subtitle, alpha thickness. I think all of that should be supported. And so that's how you change the options for a specific variable. If you want to change the global plot options, use tplot underscore options, and you just import that from pytplot. And a few of those, for instance, you can set title, change the title to MMS. You could change the X-axis margin, the Y-axis margin. There's a bunch of plot options. You could just run help on that to find the available plot options there. You can also change the figure size within a call to tplot by specifying the X size and the Y size keywords. These are supposed to be specified in inches, but if you run it on a Jupyter notebook, it tries to fit the figure inside of the cell. So these aren't going to be literally inches if you're running in a Jupyter notebook. But if you're running it on your local machine, it should actually produce a 12-inch by 5-inch figure. That's another thing I should note is that with the matplotlib backend, you can actually, if you run this on your local computer instead of in a Jupyter notebook, the figures are going to be interactive and they're going to be much higher quality. So if you're actually doing science with this, I definitely suggest running it on your local machine to produce the publication quality figures instead of trying to generate them inside of the Jupyter notebook environment. Because the Jupyter notebooks environment is going to shrink down the figures to fit inside your the cell.
Can I ask a question?
Yeah, go ahead.
Can we use the Matplotlib features like Y tick, Y label, things like that in here? For example, I want to change the ticks on the Y label in here on the previous plot. How do you do that? Can you do it in here?
The best place to go to would be to this giant crib or this giant notebook where we have examples of using Matplotlib. I think we have examples of changing the Y. So there's an option called axis font size to increase the font size. And we also have an option for increasing the character size of the Y-axis labels. But if you don't have the option, looks like we might not have those here. But at the very minimum, what you can do is set the return plot objects option to true, and it'll actually return the figure and the axes objects for that T-plot window. And then you can make whatever changes you want to the plot.
Yes, okay, thank you. And this is in pytplot GitHub, right?
Yes.
Okay,
But
thank you.
It is under the Matplotlib backend branch. So I suggest, let's see, we're at the orbit plot. At the very top of this script should have a link to that notebook right here.
Okay.
Examples.
Thank you.
Yep.
Can I ask a question about this? I haven't worked with pySPEDAS in a couple of months, but at the end of the summer, I tried a bunch of different things. I wasn't finding how to have the plots be inline in a notebook. Is this something that is newly added, or?
Yes, this is all brand new.
Okay. So if I go to it again, it should, okay, thank you.
So the thing to note is that right here at the top, this is the introduction to the new Matplotlib version of pytplot. So to get all of this, you have to install this development version from here.
Okay, thanks. I missed the first 5 minutes. Okay, perfect.
And you have to install that before you install pySPEDAS. Otherwise, pySPEDAS will go out and install the old version of pytplot.
And if I want, do I have to reinstall everything if in a new environment if I've already installed it
I
once?
suggest setting up a new environment, or you can run in Google Colab like I've been doing. So essentially, all you have to do is these commands here should get it up and running in Google Colab.
Okay, thanks.
Yep. All right, so back to orbit plots. So we have a routine that creates orbit plots. It's just you have to import it from the actual file. So there's not a shortcut for this one. So it's pySPEDAS.mms.mms orbit plot. And the function is just MMS orbit plot. If you set the time range, and it'll just go out, and there's also other keywords for probe for specifying the probes. Otherwise, if you don't specify it, it'll load the orbit plots for all 4 probes. And just like this also uses the Matplotlib. So if you generate this on your computer locally, you actually get an interactive window that you can resize and everything and zoom in. And you can also call help on this function to see the options. You can change the data rate for the MEC data that's being plotted. I mentioned the probe, you could change the coordinate plane. By default, it does X, Y, but you can also do YZ and XZ. And you could change the ranges and the coordinate system that's plotted. And it should support all the coordinate systems in the MEC data. All right, so moving on to FGM data, fields data. Loading that data is very similar to loading the MEC data. It's just pySPEDAS.mms.fgm. In this case, we're going to load burst mode data. So we set the data rate to burst, and we load all 4 probes, and we're time clipping down to this burst mode data. That way, we don't get more time than more data than we ask for. And you can see it loaded the data, loaded the variables. One thing to note is the FGM variable or FGM load routine actually, it takes the data from the CDF files. It removes data that have been flagged by the team. I think there should be a flag variable for each instrument or each spacecraft. So this contains time points which are flagged by the team, and we remove those. Most of them are, I think, are close to perigee, where the field is very, very high. And then we split these variables. Also, these variables all have the vector plus the magnitude stored. So we split those out into vector and magnitude variables. That's why you're seeing what looks like the same variable names, except with underscore bvec and btotal. So if you need a t-plot variable that actually contains a vector and not a vector plus a magnitude, then you want the bvec version of the variable. If you use our tools in IDL, it's the same thing. We do exactly the same thing. And I'm going to show how to do kilometer calculations. So we also need the position data for this time range. So I called pySPEDAS.mms.mech. We give it the same time range. We want to also use burst mode data and the same probes. And then we're also time clips so we don't get extra data. You can see it went out and loaded the data. Then we can plot the FGM data for all 4 spacecraft. And in this case, we're plotting just the B vector variables. So we don't have the B totals saved. So we have on this figure. So we have MMS1 on top, MMS2, 3, and 4. And I wanted to show also that we now have routines for calculating the cross product to the dot product of 2 t-plot variables. So you have to import those from the functions or from the module, the analysis module. So it's just pySPEDAS.analysis.t cross p, and gives you a function called t cross p. And there's also a t dot p. So using these is pretty simple to calculate b dot b. For MMS1, you just give it the b vector, and we're actually calculating the dot product of the same vector here. And it creates a new vector with the first name, and then dot, and then the second name. There's a keyword to t dot p, new name, that should allow you to specify whatever name you want for this. So you don't have to create a super long variable name. And anyway, so we created the dot product of 2 vectors, and then we plotted it using tplot. And this is the dot product of those b dot b for MMS1. And just like that, we can also do cross product. So b cross p, or b cross b. Again, it's just t cross p, and then give it the variable name, and then the second variable, second vector. And it creates, just like before, it creates a new variable with the first, followed by cross, followed by the second. And again, there's a keyword that should allow you to change this name if you want. But I'm just using the default here. And you can see the B field crossed with itself is just 0. So that's not a surprise, since a vector crossed with itself is 0. So if you want to do kilometer calculations, you just import the kilometer function from pySPEDAS.mms. You can run, again, the help function on that kilometer function, and it tells you the parameters. Let's close my mail so we stop getting emails. So you see the parameters are fields. This is a list of the t-plot variables containing the B field, and this is actually the vectors. It's going to expect the vectors here and not the vector plus the magnitude. There's also positions, which is the list of the t-plot variables containing the spacecraft position vectors. And so just for instance, since we already have the B field data and the mech data loaded, we just call kilometer, set the fields equal to the list of fields variables for all 4 spacecraft, and set the positions to the position variables for all 4 spacecraft. And it actually goes out and interpolates the data onto the same timestamps and does all the kilometer calculations and produces several variables. So on the next figure, we plot the current calculated using the kilometer technique in that previous command on top of the B field vectors for all 4 spacecraft. So you can see you have the JX, JY, and JZ. And so moving on to SCM. So if you want to say load 3 hours of survey mode L2 SCM data, note you just call pySPEDAS.mms.scm, set your time range to 3 hours. At the start, we're doing 3 hours at the start of the day, and we're time clipping down. Notice that this CDF is a daily CDF. So if we didn't time clip here, you'd get the full data, your full day's worth of data. So we're actually time clipping down to our interval here. And you can see it loaded the variable, just loaded a single variable, spacecraft survey mode, and GSC coordinates. So it can go ahead and plot that, and call tplot. And I set a couple X size and Y size keywords to make it a slightly larger plot than it otherwise would have been. And so we have routines for calculating the dynamic power spectra using SCM data. You just import TD power spec from pySPEDAS. And again, you can just call help on TD power spec, and it'll give you all the options as well as the defaults. But in this case, we're going to call TD power spec on that variable that we just loaded, the SCM B field data. And in this case, I took the defaults from our IDL crib sheet. They should also be in our Jupyter notebook for SCM as well. But these were provided by Olivier Lecontel specifically for this variable. So, if you're using burst mode SCM data, you'll want to look at either the crib sheet or the Jupyter notebook to find the actual their suggested defaults, or Olivier's suggested defaults for these options, because they're dependent on the actual the data rate and the SCM data. All right, so running TD power spec created the power spectra for the X, Y, and Z components, and they just all follow the same format, where the only difference is the X, Y, and Z here. So we can create a plot of these by just calling tplot on the string, and then just having a question mark for the X, Y, and Z. And so it just puts the X on top, Y in the middle, and then Z on the bottom. And so we have routines for adding bars to a figure. So if you want to highlight an interval, you can use the time bar function from pytplot. So you just import time bar from pytplot and give it the time. One thing to note is that you do have to give it down to the seconds, the time down to the seconds in this specific format. It's going to complain if your time format doesn't match this format. Eventually, we're going to update that and have it accept more time formats. But right now, you actually have to give it this exact time format of year, day, or year, month, day, hour, minute, seconds. So I added 2 time bars in one call here by giving it a list, or an array of times, 2 times. So it creates 2 times. And then I recreated the plot, and notice that it now has time, or vertical bars at the times that I specified in the time bar call. And there are options for time bar that allow you to change the style. And let's see, I think you can call help on this, and it should work. Should give you the options. Oops. So, change the color, thickness. So there's lots of options there. And we recently added tools for doing wave polarization calculations, T wave pol, and it should work very similarly to dynamic power spectra. You just give it the input variable that you want to calculate the polarization for. And we have a new notebook under our advanced folder called wave polarization using SCM data. So it's right here. So you just go to our SPEDAS, MMS examples, and then under advanced, it's wave polarization. And I think Safari's having trouble with those for some reason.
So you haven't updated, you haven't pushed this webinar to the MMS examples yet, right? Because I can't see it there.
Yes, correct. It's not out there yet.
Okay, you're going to do that. Yeah.
Yes, it will be after this meeting.
Okay, thank you.
Yep. And so one thing to note is that currently T-Wave poll requires NumPy 1.20 or later. So if you run into problems running this, update NumPy. I just figured this out yesterday, so I'm gonna have to resolve this dependency issue. But just if you do run it, if you run this and you run, be sure to update to the latest NumPy. And so loading EDP data, this is the electric field double probe instrument. It's just like with the others, it's just pySPEDAS.mms.edp. And the data types here, we have the DCE, so that's the DC electric field, and you can also load the spacecraft potential data by setting SCPOT in the data types. So in this example, we're loading EDP data for the time range that we did the kilometer calculations for. And again, burst mode data, and we're loading the electric field as well as spacecraft potential, and we're time clipping down to the requested time range. And then we can see loaded the variables, loaded the DC electric field data, and it also loaded the spacecraft potential data. And so we just create a T-plot window with those. In this case, we just set the X size to make it a slightly longer plot in the X direction. And you can see the spacecraft potential on top and the electric field on the bottom. And we also have data from the electron drift instrument. That's the EDI. And again, it's just pySPEDAS.mms.edi. And set the time range, and it'll go out and download the data. If you don't have it stored locally, it'll go out and download the data. If you do, it'll just load it from your local cache. And then we can plot the E cross B drift velocity and GSE coordinates. You notice that I changed the time range here from our previous default. I think I did this because there wasn't any data, or there was a problem with the data on October 16th, our standard example. So I wanted to actually have an example that includes some data. So we can plot the E cross B drift velocity and GSE coordinates. See, that was one of the variables that we loaded. And we get the E cross B drift velocity from EDI. And so one useful thing with this old time clip thing is sometimes you want to load the full day, and then instead of time clipping down, you could just zoom into a time range. It'll be a lot faster. So to do that, you use the T-limit function from pytplot. So you just import T-limit from pytplot and give it the time range that you want to zoom into, and then recreate the plot. So in this case, we're zooming into an hour of data from 1830 to 1930. And I believe this also requires this specific format to zoom in, which again, we're going to have to make it more flexible. But right now it's year, month, day, and then space, and then hour, minute, second. And you can see once I recreated the figure using the same command as before, we're now zoomed into 1 hour of data. If you want to zoom out, you can reset the full time range with the it's the full keyword, not time range, T-range keyword. It's not letting me edit it, but yeah, you set the so this should be full. The full keyword. So you set full equal to true, and then it'll reset to the full time range. And so what about the digital signal processor on the fields? So you can load the ePSD and the BPSD data from the digital signal processor. The BPSD is the magnetic power spectral density, and the ePSD is the electric power spectral density. So to load those, you just call pySPEDAS.mms.dsp, and we set some options. So we're only loading one probe one, setting our time range, and we're setting the data type to ePSD and BPSD. And the data rate here is fast, and we're loading L2. L2 probably shouldn't, probably isn't going to be required in this call, but I explicitly put it there. And we also told it to time clip. So in this case, these files are daily files and we're requesting the full day. So time clipping actually isn't going to do anything useful. It's just going to tell you it returns the full data set. So time clip is definitely not required, but it does, it at least tries to in this case, and tells you that you already have the full data set. Then we could go ahead and create a figure, the BPSD and the EPSD omnidirectional variables. See for the different directions, it has individual variables for those independent directions, and then it also has the omnidirectional BPSD and the omnidirectional EPSD, and that's what we're plotting is the omnidirectional here. And so just like before, you could use options to set various plot options for a specific variable. So to set the range, for example, to set the range for a specific axis, Y and Z, or Z, you just call options on the variable you're interested in and set the Y range option to set the Y axis range. There's also a Z range that will allow you to set the Z range, which is the color bar range. So we set, in this case, we're just setting the Y range for a couple, for those two plots, and then recreating the figure. You can see now that the Y range on the figure is updated. I also increased the X size here so that it created a slightly larger figure. You can see the times kind of get squished together down here. If you set the X size, it looks a lot better. And again, if you using these X size and Y size options on your local computer rather than in a Jupyter notebook, they should actually give you the full size. And so, and you'll also get an interactive window on your local computer that you can drag and increase the size manually. And so to load ASPOC data, finally, this is the active spacecraft potential control instrument. So again, it's just pySPEDAS.mms.aspoc and give it the time range. By default, it's going to load probe 1 survey mode L2 data. So it loaded the ASPOC data, and we can plot the ion current for ASPOC instrument. You see it comes on somewhere around 1330 or so. So ASPOC was turned off before then, and after around 1700 or so, it's turned off again. And so moving on to the FEEPS and EIS, this is the energetic particle detector data. Just like all the other instruments, pySPEDAS.mms.FEEPS load the FEEPS data. By default, it loads the electron data, so you don't have to specify the data type of electron. By default, it also loads this day, 2015, or the October 16th from 2015, but I wanted to be explicit with my time ranges. And it also will load survey mode by default. But in this case, we're loading probe 4. If you don't specify a probe, it'll load probe 1. And so just like with our IDL routines, we do a bunch of processing or post-processing once we load the data for FEEPS. The best way to figure that out is, or to see all of the processing, is probably to go to our MMS folder and look at the README, because we have a list of all of the processing that happens, including the FEEPS and EIS. Omnidirectional spectrograms are calculated from the individual telescope data. See, they're spin averaged. Sun contaminations removed from FEEPS before it's created. We split off an integral channel from the variables. And so I think we also have flat field corrections, bad energy tables and or bad energy and bad channels are removed from the team or from tables suggested by the or specified by the team.
Please, can I ask a question?
Yeah, go ahead.
I am trying to access this page, but what I am seeing is the other page you just left now. So you just.
So this one?
Yeah, this is what I am seeing. I am not seeing the PyT plot page.
Yeah, so for this, I'm at the pySPEDAS under the MMS folder. So if you go to SPEDAS and then pySPEDAS and then pySPEDAS, and then you go to MMS, and there's a README in there that includes what's included for MMS. And it actually kind of looks like some stuff might be missing.
I am actually talking about the PyT plot page.
So
Yeah, so can you just guide me on how I can get to this point? I actually missed it at the beginning of the whole.
yeah, so if you go to the PyT plot, actually it's going to be at the top of, there's going to be a link at the top of this, but since that's not available yet, the easy way is to just go to the PyT plot repository. So let's open that. And then under the branches, you have to change to matplotlib backend. And then go to docs. It's under the docs folder. And then it's PyT plot examples with matplotlib. And I do have a link to this file at the top of this presentation. So it'll be available after the meeting.
Okay, okay, thank you.
And the place it'll be available is our MMS-examples repository under the webinars folder. All right, so in this case, we loaded survey mode L2 electron data from FEEPS, and it did a bunch of post-processing on those variables, and it created, you can see it removed the sun contamination, and it actually returned an omnidirectional spectra as well as the spin average omnidirectional spectra. So we went and created the plot of the spin averaged omnidirectional spectra. And just like before, you can use get data to return the data values for these. Just as before, data, when you call get data, it'll return a variable called data here, and it's a named tuple, and data.times would be the times, data.y are the actual data values, and data.v in this case are going to be the energy values. So that's the actual y-axis values that the data values specified in data.y are actually put at. So you can see data.v only has 15 values, so that's 15 energies, and you can just print the energies off by calling data.v. And some of these energy spectra, not for FEEPS, but for FPI, is actually time varying. So you could get a time varying energy table here if you call this on a FPI variable. And we might show that later. If not, there's an example in our examples notebooks that should show a time varying energy table. But again, the y values are just data.y. So you can see the data.y.shape. It's 2,800 times and 15 energies. And of course, these are those actual 15 energies. We want to look at the values at a specific time. We can tell it. So this is the 1002 index, and then give it for all energies. So if you were interested in, for instance, the time or the actual time for this specific, so we have the data values and we have the energy values. You could also get the actual time values by saying times and then give it a time index. And so that's the Unix time. And of course, we could also convert that to a string using time string. So this is the these are the values, and then this is the energy at this specific time for FEEPS. Just like with so we also have routines for calculating the pitch angle distributions once you have the data loaded, the FEEPS data loaded. So you just import MMS FEEPS pad from pySPEDAS, and just like with the load routines, we have a bunch of defaults for the options. since we loaded probe 4, we actually have to change the probe to 4. Other than that, we're just using the defaults, which is electron data energies from 70 to 600 keV, and the bin size of around 16 degrees. And again, you can call help on this to get all those options in the defaults. But in this case, we're just importing the function and calling it on probe 4 to go ahead and create the pitch angle distributions for probe 4. And so you can see it did. So it created 2 variables, one just the pitch angle distribution, and then one with the spin average pitch angle distribution. And we go ahead and call tplot on those figures and plot the non-spin averaged on top and the spin averaged on the bottom. EIS is very similar. You just call pySPEDAS.mms.eis. We set the data type. In this case, the data types are EXTOF, that's the energy by time of flight data, and PHXTOF, that's pulse height by time of flight data. So we set a time range. I'm not sure why I used this specific time range for EIS. And so the data rate by default, it's going to use survey mode. So this really isn't required. And probe 4 by default, it's going to use probe 1. So we're changing the probe to 4 here. And just like with beeps, we create the spin average. We get the omnidirectional variables, as well as the spin average omnidirectional variables. And so we can call tplot on the new variables. So in this case, we're plotting the spin averaged omnidirectional variables with the energy by time of flight data on top and the pulse height by time of flight data on the bottom. Again, we're just plotting proton flux. They have other species here like helium, oxygen, but we're just showing up the proton flux here. And just like with FEEPs, we have EIS pitch angle distributions. So you just import MMS_EIS_pad from pySPEDAS, and has defaults just like the FEEPs version does. So it defaults to survey mode, and it also defaults to energy by time of flight data. So if we wanted to actually calculate the pitch angle distribution for pulse height by time of flight data, we would have to say data type equals pulse height by flight. And that would generate the pitch angle distribution for that data type. But since we called it without that data type keyword initially, you can notice that it created the pitch angle distributions and the spin average pitch angle distributions for the energy by time of flight data. And we could just go ahead and create a figure using that. So we show the spin averaged omnidirectional flux on top, and then we have the energy by time of flight proton pitch angle distribution spin averaged on the bottom. And for the full time range, I think, or for the full energy range, there's also it also creates the omnidirectional spin averaged pitch angle distributions at smaller energy ranges as well. But for this case, we're actually plotting the full energy range available. And so that's pretty much it for the EPD data. Moving on to the plasma data, that's the FPI and HPCA. There's one really important thing here that I need to point out for FPI and HPCA. These data products and their CDFs are stored at the beginning of the accumulation interval for the instrument and not at the middle of the accumulation interval. So you really want to set this center measurement keyword to true, because that will move everything or shift everything to the middle of the accumulation interval. And if you ever do any analysis with FPI and any other instruments, or HPCA and any other instruments, you want to compare apples to apples, because all the other instruments like the FGM data, those are actually at the middle of the accumulation interval. So you're going to want to center these measurements to have them all on the same epoch, essentially. So if you're calling the FPI load routine, be sure to remember the center measurement keyword. And so the T range keyword is just like before. And again, we're using probe 4 instead of the default of 1. And for, in this case, we're loading the moments data. So we're loading set data type to DIS-moms and DES-moms. So that's the ion moments and the electron moments for this full day here. So you can see it went out and grabbed the CDF files, the ion files, the electron files, and it loaded them into memory. And it also time shifted everything to the middle of the accumulation interval, since I specified that center measurement keyword equal to true. So we can then call tplot on a few of the variables. We have the ions energy spectra, omnidirectional ion energy spectra, and we have the ion bulk velocity and GSC coordinates in the middle. And then we have the ion density on the bottom. Notice that sometimes there are pretty big gaps between the different panels. There's an option in tplot options that allows you to change that called vertical spacing. So you just, we actually loaded, or we imported tplot options from before and used it to set the title and the X margin. So now we're gonna we already have it imported. We just call the function, give it the vertical spacing option. And this time it's something very small. And then recreate the exact same figure. And you can notice this time the vertical spacing is much smaller. You set it to 0, it'll put them on top of each other. And so for HPCA, see, I've already made the mistake myself. Center measurement keyword for HPCA, that should be there. So when you're loading HPCA data, just like with the others, it's pySPEDAS.mms.hpca. And again, just like FPI, you have to set that center measurement keyword to move everything to the same time scale. So to essentially shift everything from the beginning of the accumulation interval to the middle of the accumulation interval. And we set the data type equal to moments to load the moments data. So it's temperature, velocity, pressure, stuff like that. And by default, it's going to load probe 1. So we're just going to specify probe 4 to show how to set a specific probe. And it went out, grabbed the files and loaded the data into memory. Then we can, again, create a tplot window just by calling tplot on the variables you're interested in. So we have the H plus number density, H plus bulk velocity, H plus scalar temperature, H plus ion pressure. And so in this case, I wasn't entirely sure what the H plus ion pressure actually is. So I used get data and set the metadata option equal to true. So I wanted to return, the idea here was to return the CDF metadata so that I can actually see what the team put in the CDF for this variable, what it actually contains. And so once we have the CDF metadata for the ion pressure, of course, if you don't include the CDF key here, it'll show you all the CDF metadata as well as the plot metadata from pytplot. But we're limiting ourselves to the CDF metadata, and then in a subset of the CDF metadata, they have the global attributes, which is GAT, and they have the variable attributes, which is VAT. So if you're familiar with CDFs, this is just standard CDF and VAT. So this is the variable attributes for this particular variable as stored in the CDF file. So you can see it's the ion pressure tensor for hydrogen plus for each half spin. And I suspect these are the components of the tensor. And then each one is one of these lines. So you could run options and set legend names to these, and it should add a legend with the legend names. So essentially that's the pressure tensor and the different components of it. And so what about like flux and phase space density? So again, you just call pySPEDAS.mms.hpca. And this time you want to set the data type equal to ion instead of moments, because the phase space density and the flux are in a data type called ion. And I didn't include it here, but I should have. Again, should have been center measurement equal to true there. Let's save that. right? And so one thing to note about these, the phase space density and the flux stored in these ion files for HPCA, so they're a function of energy and angle. So if you actually want to calculate an omnidirectional data product, you have to average over either average or sum over the field of view, and then spin average the data. So for flux, what you do is you just call, so to do that, we have routines called MMS HPCA calc A nodes and MMS HPCA spin sum, and these work just like they do in IDL once you import them from pySPEDAS. So you can call MMS HPCA calc A nodes, give it the probe number. By default, it's probably going to do probe 1, and give it the field of view. So this, in this case, it tells it to average over 300 or 0 from 3 to 360, so the full field of view. And then for an actual omnidirectional data product for HPCA, you also have the spin average. So we have a routine called MMS HPCA spin sum. And if you don't specify the average keyword, it'll sum over the spin instead of averaging. But if you set the average equal to true, it'll actually do a spin average. And then it creates variables with the underscore spin. So you have elevation 0 to 360, and then underscore spin for the spin average. And that should be the full omnidirectional data product, or energy spectra in this case. So we plot the H plus flux. This is the full omnidirectional H plus for HPCA. And we also have a notebook that shows how to do a bunch of plasma calculations using MMS Data Plasma Pi. This turns out to be super useful because you can do tons of plasma calculations with this package. So I wanted to show that off. Actually, we should load this in here just in case. Problems loading in Safari. So we don't install Plasma Pi by default. So when you run this crib sheet, you'll have to install Plasma Pi with a pip install Plasma Pi. But I show how to load FGM data, load FPI data, and then you can interpolate the various variables onto a common set of times using t-interpol. And you can extract the data values, calculate the total temperature from the parallel and perpendicular. By default, the FPI temperatures are in parallel and perpendicular components. So to calculate the full temperature, you just have to use those components to calculate that using the equation available in their data products guide. You can add units to the data using AstroPi units. So you just import units as U from AstroPi, and then multiply the units that you're interested in by the data product. So for instance, to add the units to the B field data, we just say the B field variable dot y times units dot nt, and it'll actually add units to that variable. And so we also add the units to the density and the temperature, and then we import Plasma Pi, and then we can calculate a whole bunch of stuff using those the B field and the FPI data. For instance, the alphane speed, plasma beta. We calculate the ions plasma beta, the electrons plasma beta, and then combine them. You can calculate the ion inertial length, the bond length, ion gyro frequency, gyro radius, lower and upper high frequencies. And then we finally show how to save them in the variables, plot metadata, and actually create a figure. So I think this is going to be super useful for people. I didn't want to include an example in this because it probably would have taken too long to actually walk through all of that. But that's essentially, if you want to do plasma calculations, I suggest looking into Plasma Pi first before implementing the algorithms yourself, because they have a lot of stuff in there and it's easy. You just have to load the data with pySPEDAS, extract the data, add the units to it, make sure it's all in the same timestamps, and just pass the variables off to Plasma Pi, and it does the calculations for you. All right, so finally we have MMS part get spec. So this is still experimental. I'm still testing it. But the idea here is that you should be able to generate the spectrograms, both the energy spectrograms as well as the theta phi, that's the angular spectrograms, as well as the pitch angle and gyro phase spectrograms and moments directly from the FPI and the HBCA distribution functions. And so this should work just like it does in IDL. So if you're familiar with our IDL tools, you just, the major difference is that you have to actually import MMS part get spec from the pySPEDAS.mms.particles folder. And then you just call it, you give it the time range, you give it your species, give it a probe, and then give it the output options. Right now, the supported output options are energy, that's the energy spectrogram, that's the theta spectrogram, phi spectrogram, then PA is the pitch angle distribution, it's the pitch angle spectrogram, and then gyros, the gyro phase spectrogram. And of course, moments are the moments, so it's density and temperature. And what it does is what that single command is, it goes out and it downloads the distribution data. And by default, it's going to use FPI, but if you change, you could also say, change the instrument to HBCA and change the species to H+. It would do the same calculations for HBCA, H+. Essentially what it does is it goes out and grabs the data. It grabs the support data, like the MEC data in this case. And it also grabs the B field data. It's going to use that for the field aligned coordinate transformation. So this, it uses that to calculate the pitch angle distribution and the gyro phase distribution. And then it went out and grabbed the spacecraft potential. And in some cases, it grabs more data than it should right now. It's still experimental. I think we should be loading certain types of data only in certain cases, but in this case, we're loading all of the support data, so it's there in case we need it. And then it does the calculation for the full time range. And you can see right now it's taking a really long time to do the calculations. I suspect that you can speed these calculations up pretty drastically by installing Anaconda and running it on a Anaconda installation rather than a pure Python installation. Because we have there's a library called Bottleneck that implements several of the NumPy functions in C. And if you install Python using Anaconda, you get Bottleneck by default. If you don't install, you have to, and if you don't install Python using Anaconda, then you probably won't have Bottleneck installed. And I think with Bottleneck, it's 2.5 to 3 times faster to do most of the calculations. And that's not just with these distribution functions, it's also with calculating the EIS and the PEEPS pitch angle distributions. Those calculations go a lot faster if you have Bottleneck installed, which you can get, again, just by installing Python with Anaconda on your machine. So once this finished, I went ahead and created a figure. I plotted the energy spectra, theta spectrogram, phi spectrogram, pitch angle distribution, and the gyro phase distribution. So again, we have the energy spectra, theta, phi, pitch angle, and gyro phase. You might notice these Y titles are going to be changed soon. Energy and EV should be dropped down to the next line. Originally, so in the Qt version, this backslash actually drops things down to the next line. That's why you see a backslash there. And the metadata is still actually being set for that old Qt version right now. I need to update that. But again, you have the energy spectra, theta spectrogram, phi spectrogram, and then pitch angle distribution, and then gyro phase distribution. And I didn't create a plot of the moments. Since I ran this in the previous time, we're not going to have the moments already loaded. But it did create the density, flux, velocity, average temperature. So did create the moments, but I doubt they're still stored at memory right now, so I can't actually create the figure. I should have created those last night. So finally, I went ahead and attached another, I think this is pretty useful, being able to save figures, another section. Previously with the Qt version of pytplot, you could only save PNGs, and they were pretty low quality PNGs. But now with this new version, you can save PostScript, SVGs, or PDF files, and they all look really nice when you save them. So to save these, you just give it the keyword. So in this example, we're saving the PNG file, calling it my file, and give it the list of tplot variables you want to create. And so it created this window. And then since I specified the save PNG, it created a PNG called myfile.png. That should be in here somewhere. Usually you can click this to actually get the file. Looks like oh, there it is. Oh, gone again. So if you're saving the figures, I definitely suggest running this on your local computer rather than running it in Google Colab. Because it's going to be a lot easier to just save it to your local computer. But it should create the file in this file directory. For some reason, it won't let me open it. But that my file is going to be in your local working directory, and it's going to have .png added to the end. But if you use save EPS, it's going to be .eps. Save SVG, it'll be .svg. Again, save PDF is going to be .pdf. All right, so that's pretty much all I have. I was expecting it to take an hour, so an hour and 20 minutes isn't too bad. I'm going to upload this again to the repository. I want to show again where you can actually find this. Just go to our top level SPEDAS repository on GitHub. It's github.com/SPEDAS, and then MMS examples, and then webinars. And it's going to be in this list. There's going to be a fourth one added right after this presentation. I just got to upload it. And so that's all I have. Any questions? I'm also going to upload this to our YouTube. So just Google SPEDAS YouTube if you want to find it. And so that's all I have. Thanks for calling in. And as usual, email me if you have any questions. My email is going to be at the top of the script. And cool. Thanks for calling in.
Hey, Eric, can you hear me?
Yeah. Okay. Thank you. Thank you, Eric. Thank you.
Yeah, agreed. Thank you. Awesome. Yeah, I was wondering, I haven't heard any updates on making the matplotlib version like the official replacement. Has anything been made on that?
I haven't heard anything yet.
That's fine.
I'll probably just bug Brian about it. He's probably busy because the holidays and everything. AGU.
Yeah.
But yeah, for now we're just using the experimental version and developing that. But I suspect once Brian can actually get to it and review it, he's probably going to be very supportive of it being the official version. And then we can eliminate having to install it from the repo directly here.
Yeah, good stuff.
Great. Thanks for calling in.
Thanks, good.